In this video, we're going to talk about some theory about the curve called hyperbola, and we're going to try to connect the video of the kind of not so easy to understand way in which the hyperbola is drawn to the equations that we're going to work with. If you are not so interested in the theory, you can skip this video and go right on to the next video where we will start working problems. And in those segments, I'll give you all the details that you need to know to be able to solve the problems. In this video, I'm going to focus on trying to explain a little bit where the equation of a hyperbola actually comes from. So let's start talking about a hyperbola. Again, I hope you've already watched the video where you see using a string and a straight edge, you can draw a hyperbola. It's quite a bit more complicated than drawing an ellipse, and I don't know if just in a video segment I could describe it without drawing my own. Here, I'm not going to draw one. We're just going to start moving toward the equation. And you want to know right off the bat that a hyperbola is a special curve with two branches, so very different from an ellipse. It's not in one piece. Every hyperbola has two separate branches, and every hyperbola has two straight lines that are related to it called asymptotes. They're like the asymptotes of a rational function that we've talked about before. They're normally not going to be horizontal and vertical, though. And they're not actually part of the hyperbola, but they help us draw the hyperbola and they help us understand the hyperbola. So there is a connection between a hyperbola and an ellipse, because the technical definition of a hyperbola goes like this. A hyperbola is the curve formed by all points in the plane for which the difference of the distances from two fixed points is constant. So those two fixed points, again, we're going to call foci. Each one is a focus, right? So our F and our F prime are the foci. And yet here, we can't talk about a string in quite the same way, because we're saying points are on the hyperbola if the distance from one focus minus the distance from the other focus is equal to some constant. That constant is some number picked out ahead of time. Could be 5, could be 7, could be any number, but once you pick that number, every point on the hyperbola satisfies this distance difference, satisfies that for that point. And here, what's different from an ellipse is in an ellipse definition, we had the word sum here. We said the sum of the distances was constant. Now we're looking at a situation where the difference of the distances is constant. And when you change to the word difference, you get this totally different kind of situation. Now, let's start talking about some of the vocabulary attached to a hyperbola. So here's another example. Sometimes the hyperbola has two branches that are sideways. Sometimes they're up and down, one above the other. Here's an example where the branches are sideways. Right at the very center of the picture is something we call the center of the hyperbola. It's actually where these two dotted lines cross. It's where the two asymptotes cross. If I draw a line, if I imagine going straight across from one focus to the other, I touch the hyperbola at 2 points, one here and one here. Each one of those points is called a vertex. So there's a vertex here and a vertex there. And if you connect up the two vertices, that line that I just drew is called the transverse axis. We'll be able to write that out again. Transverse axis connects one vertex to another. Now, right on, in line with that are the two foci, right? So here's a focus, but they do not, when we talk about the length of the transverse axis, we only go from vertex to vertex. Now let's talk about a little bit about how some of these distances are related. So we're going to give some of these distances a name. The distance from the center to a vertex we're going to call A. That's always going to be some number for a given hyperbola. And the distance from a focus to the center we're going to call C. So A is actually 1/2 of the transverse axis, because it's 1/2 the difference from one vertex to the other. And C really has the same meaning that it had with ellipse. It's a distance from the focus to the center. C is always larger than A, because C always is a greater distance than the A distance. Oh, by the way, I plunged right into things, and I forgot to, I want to just mention something, that a lot of what I'm talking about here is on the handwritten handout that starts where it says just ellipses at first. And I think we already went through, there's like several pages of ellipse material. But when you get to page 4 on that handwritten handout that's posted in Canvas, you start getting to the hyperbola information. And basically what I'm doing here is I'm just talking us through some of these details about hyperbola that are written on the handwritten handout. So if you want more depth, you can look at the handwritten handout that starts out with ellipses, continues with hyperbolas on page 4. I'm just trying to summarize things here in this video segment as we go through. And again, that handwritten handout, if you don't want to get into it, you don't have to. We'll focus on what you absolutely need to know in a future video. So now I'm going to continue on here, and let's talk a little bit more about where the equation of a hyperbola might come from. So I drew a couple more pictures. So here's just a hyperbola with that distance idea, right? Where d1 from the focus to a point on the hyperbola minus d2 from the other focus to a point. That difference is some constant. Call that the constant difference, some number for each hyperbola. But if I imagine looking at the distance to this vertex from each of the two foci, d1 looks like this, d2 looks like that. Now the vertex is on the hyperbola, so d1 in this picture minus d2 has to equal that same constant. Well, d1 goes from one focus all the way through the center over to here. If we subtract off d2 from d1, well, that's like subtracting off the distance from the focus to the vertex on that side, right? So if we take d1 and subtract from d1 a piece that's equal to d2, what we're left with is just the length of the transverse axis. And we just said a moment ago, A is half of the transverse axis, so the total transverse axis length is 2A. So that constant difference is equal to 2A, which is equal to the length of the transverse axis. Okay, now we're going to try to generate an equation for the hyperbola. And I'm going to label several things in my picture here. We're introducing a coordinate system, x and y coordinate system, and we're going to put the center of our hyperbola at 0, 0. And we're going to put, for now, we're going to put the transverse axis on the x-axis. So the vertices and the foci of the hyperbola lie on that the x-axis. Now, the letters A and C have the same meaning that we talked about in just a couple pictures ago here. So the A and the C I can now label, I can use as coordinates of points in my xy coordinate system. So this focus here is going to be C0. This focus is going to be negative C0. And this vertex, and maybe I'll put an arrow since it's hard for me to write right in there. This vertex is going to be at the point A0. This vertex is going to be at the point minus A0. And if we pick any point, on the hyperbola, what we want to be true is the distance from one focus. So I'm just going to let this be, let x, y denote any point on the hyperbola. So this is maybe my d1 distance here. This is going to be my d2 distance here. And so what's got to be true is that d1 minus d2 is always going to be equal to, let's see, how can I express those distances? Well, let's write this in blue. The distance from negative C0 to xy minus the distance from C0 to xy. I can write these expressions out as distance formula expressions. I get x minus a negative c squared plus y minus 0 squared minus another square root, x minus c squared plus y minus 0 squared. And now that distance, that constant distance, we said always has to equal 2a. It has to be equal to the length of the transverse axis, the distance from one vertex to another. So here's the start of our equation. Just like with an ellipse, it takes lots of steps of algebra to try to simplify this thing, and I'm not going to write it out right here. And what we get to, though, is the following. X squared over a squared minus y squared over c squared minus a squared equals 1. So we actually get a form that looks very similar to an ellipse equation in a way. And we're going to make a little change here. Now we don't have a b constant yet, but we've talked about how c is always greater than a. So c squared minus a squared must be positive. So we're going to let b be a number such that b squared is equal to c squared minus a squared. So what we could just, so what's b? B is the square root of c squared minus a squared. But we want to be able to say, it's convenient to be able to say that this positive denominator, has to be positive, is actually b squared. So then we can write the equation in the simpler form, x squared over a squared minus y squared over b squared equals 1, where this relationship holds, where the b squared equals c squared minus a squared relationship holds. So that's, again, I didn't really fill in the details, but that's really the idea behind where the equation for a hyperbola comes from. And it's extremely similar to the equation with an ellipse. In fact, the only difference is the minus sign in the middle. So it's kind of interesting that just that difference, that minus sign, gives us a hyperbola instead of an ellipse. An ellipse will have a plus sign in the middle. A hyperbola will have a minus sign. Now, I just want to say a little bit more before we finish up on this. A couple more things. And one is, what if we put the hyperbola in a more of a vertical position here, where we put the center at 0 again, 0, 0, but the transverse axis on the y-axis. So the coordinates now of the foci are going to be 0 x-coordinate, c y-coordinate, 0 minus c, since they're on the y-axis. And here are the two vertices of the hyperbola. They're now going to have coordinates 0a, 0 minus a. And all I'm going to do is same thing we did with an ellipse. I think when we talked about this, I'm just going to give you the form of the equation that we get in this case. The equation ends up being y squared over a squared minus x squared over b squared equals 1, where that b squared again is equal to c squared minus a squared, just like on our previous page. So there's a little bit of a difference here. When we go through examples, we'll see what the difference is. We got to learn how to tell the difference between a hyperbola that has its axis, transverse axis on the x-axis, and one that has its transverse axis on the y-axis. And we'll talk about that some more in some examples. And now, one more thing though, because something an ellipse does not have that a hyperbola does have are asymptotes. And I want to just make a few comments here, and then we'll wrap things up and we'll move on to some problems. But the question is, if you start with the equation like x squared over a squared minus y squared over b squared equals 1, what are the equations of the asymptotes? How do you find the asymptotes? How do you know how to draw them? And so here's how you can find the equations of the asymptotes. Through many steps, this form of the equation can be transformed to this form, y equals plus or minus b over a x times the square root of 1 minus a squared over x squared. And we've seen that, you can see that on the handwritten handout on page 6 of the handwritten handout. I have all those details spelled out for you, okay? I'm not going to go through those details here. You can read those over on your own. And why would anybody want to look at this form? Well, it's a horrible mess, but it gives us a way to think about where the asymptotes come from, because as x approaches infinity or minus infinity, so as x gets very, very large or very, very negative, this fraction, a squared over x squared, is going to approach 0 because the denominator is blowing up and getting huge. So it's this fraction in the expression that will be approaching 0. So y equals plus or minus b over ax times the square root of 1 minus a squared over x squared approaches y equals plus or minus b over ax times, the only change I'm making here is that a squared over x squared gets replaced with 0 because that part of the expression is approaching 0. Now, that simplifies things quite a bit here because that whole square root now becomes the square root of 1, which is just 1. So all I'm left with is plus or minus b over ax times 1. And so this is sort of the moral of the story is as x approaches plus or minus infinity, it's not easy, but one can show that y will approach plus or minus b over ax. And so that means the asymptote equations are y equals b over ax and y equals minus b over ax, where a and b are those constants that appear in the equation of the hyperbola. And again, we'll look at this more with specific examples in just a bit. But these are line equations. These are like of the form y equals mx plus b, where the y-intercept is 0. So the b over a, or the minus b over a, is the slope of the asymptote. And both asymptotes intersect the y-axis at 0. So it turns out we're going to use, so where we're headed is we're going to use something called the conjugate vertices, or co-vertices as our textbook calls them. And we're going to use something called the central rectangle to help us draw the asymptotes of the hyperbola. So again, we don't need this theoretical discussion. I just wanted you to see some of the math behind where those asymptote equations come from. In the problems that we start working on next, I'll show you my quick and easy way to draw the asymptotes and draw the hyperbola. So problems are next.